Hello everyone, welcome to the SWAM NPTEL course on Mathematical Geophysics. We continue with module number 7, Thermofluidic Processes in Geophysics. This is the third lecture in this module titled Mantle Convection. In this lecture, the concepts covered are related to convective heat flows in the mantle. In the mantle, we would be going through the various types of heat flows divided into 5 components which are presented in this lecture. First, the concepts of heat flow. Second, mantle convection models. Third, the mantle convection equation. Fourth, the various non-dimensionalization processes. And 5, the material properties which affect mantle convection. So let us begin. First, we look into the concept of heat flow in the mantle. Now, as we have discussed in previous lecture, mantle is highly viscous. So, the convective heat flow in the mantle occurs through convection as well as conduction. So, convective heat flow in the mantle occurs predominantly, while conduction also is prevalent, although the conductivity is so less that the conduction is not as significant as convection. In the mantle, the convective heat transfer process transfers heat from the core mantle boundary towards the surface, that is the crust. The convective heat flow in the mantle occurs through slow, continuous movement of semi-solid rock which is occurring in the mantle. This behaves plastically over geological time scale. The geological time scale ranges from million to hundred of millions of years, which is the time period of overturning of the material in the mantle. Next, we look into the sources of the heat which is there in the mantle. There are 3 sources of heat in the mantle. First, the residual heat from the accretion of planetesimals and differentiation of the earth during its early formation. This is the trapped heat. Next, the heat which is produced by the decay of radioactive isotopes such as uranium, thorium and potassium 40. These are the generative heat. Finally, we have the heat which is transferred from the Earth's core into the mantle. Thus, we have the trapped heat, the generated heat, and the transferred heat which add to the sources of heat in the mantle. Thus, if we consider this as the mantle, then we have the entrapped heat shown by dotted regions. We have generative heat which is occurring due to radioactive decay and the transferred heat from core to mantle. Now, the mechanism of mantle convection. Mantle convection is driven by thermal gradients. The thermal gradients occur due to the difference of temperature from deeper layers in the mantle to shallower layers of the mantle where the temperature is lower. The hotter and less dense rock at the deeper regions rises towards the surface, while cooler and high density rocks at the surface and shallower regions moves towards the deeper regions of the mantle. This movement of denser rock towards the core mantle boundary and movement of lighter rocks away from the core mantle boundary creates the convective overturn cycle of the mantle. Next, we have the viscosity. The viscosity is the resistive force of mantle convection. It resists the flow of mantle fluid or highly viscous solid throughout the convective cycle. However, due to such highly viscous flow, the mantle acquires its unique convective signature, which is slow, tedious, and continuous movement of the rock. The high temperature regions in the mantle semi-solidifies the rock and the rock becomes partially molten and soft. This allows deformation of the rock plastically and creates a shearing effect and convection currents. Few features of the mantle convection are large scale convection, which are large regions of overturning material cycles. Then there are smaller localized upwelling zones. These upwelling zones are near the core mantle boundary, and also there are downwelling zones which are located at shallower regions of the mantle. The mantle convection is dominated by advection and conduction. Heat is primarily transported through advection, which is the transport of high temperature materials and low temperature materials, which carry the thermal energy with them. This is material transport. Also, there is conductive heat transfer. The conductive heat transfer does not require transport of materials. However, it is only significant in shallower regions, which is near the lithosphere or the upper regions of the mantle where the material is solid. Now we look into the various models of mantle convection. So there are three main models of mantle convection. One is the whole mantle convection. This model assumes that the entire mantle convects as a single unit. A single unit or a single cell convective cycle moves material from the core mantle boundary up to the lithosphere and back. There are no intermediate cycles. This diagram illustrates the whole mantle convection. We have the core below and the lithosphere at the top. Note that there are only single large-scale cycles of mantle convection. These are single-cell convective models. A more advanced model of mantle convection is the layered convection model. The layered convection model assumes that the mantle convection occurs in different layers. These layers are separated by material properties. For example, This diagram shows the layered convection model in two layers. There is this first layer which is closer to the surface and is smaller than the second layer which is deeper inside. The first layer has a different material property of the materials than the second layer. Hence, the total convection is being divided into two layers. This is a dual cell layered model. There can be more than two cells or two layers in a layered convection model. The third mechanism of mantle convection is plume-driven convection. Plume-driven convection means that convection is being forced from the core mantle boundary surface. This is illustrated using this figure. Consider this plume. This plume occurs when a small region near the core mantle boundary becomes excessively hot and it unstabilizes and forms the plume. This plume then rises throughout the mantle up to the surface or the lithosphere. You can see that in this diagram there are various plumes at certain stages of evolution. This is a new plume. This is an extinct plume which shows that the plume had evolved towards certain time after which it got destroyed. This is an established plume which has completed its cycle and its evolution right from its generation at the core mantle boundary up to reaching the lithosphere. Now, the plume-driven convection model also has the downwellings or movement of cold, denser material from top to bottom. This is occurring through subduction slabs. These are subduction regions. An evolved plume gives rise to hotspots or volcanic islands. There are many occurrences of volcanic islands that can be observed on the Earth's surface. For example, Hawaiian Islands. These islands are evidence that such type of plume-driven convection occurs in the mantle. Other evidences which are occurring on the surface of the earth and observed that give justification for plume-driven convection are the formation of ridges such as the mid-oceanic ridge, volcanic chain mountains, andesite volcanoes, island arcs, etc. These are very unique geodynamic signatures which are supporting plume-driven convection model of the mantle. Now let us go further to derive the equations for mantle convection. The equations for mantle convection involves governing equations for fluid dynamics, heat transfer and thermodynamics. We invoke the unique conditions of the Earth's mantle. They are inherently complex and the mantle's high viscosity affects the motion of fluid and fluid-like solid rock. These models are inherently very complex, adapting to mantle's high viscosity and the material properties and large-scale geometry. So let us look at the mathematical expressions for the governing equations. First, we have the divergence of u equals 0, which represents the continuity equation or conservation of mass. Secondly, we have the momentum conservation equation or Newton's law of motion. Here, the high viscosity fluid requires a low Reynolds number regime, which means that there is no inertial term. That means the del u by del t term, which is present as acceleration term, is negligible. This leads to negligible inertial forces compared to highly viscous and highly buoyant forces. Thus, we have the net force equals to 0. There are no inertial term or mass into acceleration term on the right hand side because of the slowly movement of materials owing to high viscosity. We have on the left hand side the first term is the pressure gradient, the second term is the viscosity, and the third term is the buoyancy term. Note that the viscosity term includes the viscosity coefficient nu inside the gradient operator. This is because nu is spatially dependent. Finally, we have the conservation of energy. The conservation of energy is also equivalently known as the heat transfer equation. As we know, both conduction and convection heat transfer occurs. This gives us del T by del T, which is the evolution of temperature through time affected by convection process given by this advective term, which is u dot grad u, the conduction process, which is given by kappa Laplacian of T, and any other heat generation process given by h by rho Cp. These are the advective, conductive, and enthalpy related heat generation and heat transfer processes. These three terms can be written as the advective, conductive, and the radioactive processes of heat transfer. Here K, rho, Cp are fluid properties and H is heat source or heat sink. This is the heat transfer equation and the third equation in the governing equations for mantle convection. Now, modeling and solving these convective equations for mantle requires non-dimensionalization. The non-dimensional process makes the equations in a form which is more relevant for understanding the physical mechanisms and parameter regime dependence of the solutions. This non-dimensionalization process involves various scaling factors with which the quantities are scaled. For example, the length scale is given by d, that is the thickness of the mantle. The time scale is given by the thermal diffusion time scale. The temperature is scaled by delta T, which is the temperature difference across the mantle. The velocity scale is given by K by D. The non-dimensional control parameters are Rayleigh number and Prandtl numbers. These Rayleigh number and Prandtl number denote the effect of buoyancy and material properties respectively. The Rayleigh number is the ratio of buoyancy force to viscous resistance, while Prandtl number is the ratio of viscous diffusion to thermal diffusion. Particularly for mantle, since the viscous diffusion is much higher, thus the Prandtl number tends to infinity for the highly viscous mantle. Next, we come to the various boundary conditions. The boundary conditions are useful to constrain the solution of the partial differential equations which govern the mantle convection. The thermal boundary condition is fixed temperature at both the boundaries or fixed heat flux at one of the boundaries. The mechanical boundary condition is no-slip boundary conditions where the velocity is set to 0 at the top and bottom boundaries of the mantle. Alternatively, we can have the stress-free mechanical boundary conditions where the stress or the normal derivative of the velocity goes to 0 at the boundaries. The heat transfer is estimated using Nusselt number, which is a non-dimensional number quantifying the convective process dominance over conductive process. It has been obtained through rigorous studies that Nusselt number varies as Rayleigh number to the power 1/3, which means as the Rayleigh number increases, the Nusselt number increases. In other words, stronger buoyancy forces would lead to higher convection and convective dominance in the mantle. For more information, we have put aside a table. This table lists the various properties of matter and the units and quantities of various physical quantities which are related to mantle convection. One can go through them for reference. Now we move on to the material property dependent mantle convection. The material property of viscosity changes throughout space in the mantle. The viscosity in the mantle is also dependent on temperature, given by nu as a function of temperature equals nu 0 e to the power capital E by RT, where E is the activation energy and R is the gas constant. Now, depending upon high and low temperature regions, mantle convection experiences higher or lower viscous resistivity. Let us consider the diagram for more understanding of this material property dependent mantle convection. Here one can see that the temperature are given by the color. Regions of high temperature are shown in red while colder regions are shown in blue. Where the temperature is high, in those regions the viscosity is lower. And in the colder regions the viscosity is higher. On the adjacent diagram, the temperature and viscosity is shown. With height from the core mantle boundary, the temperature changes as shown here. This leads to the change of viscosity with height. Higher temperature leads to lower viscosity. And lower temperature leads to higher viscosity. Thus, mantle convection is to be simulated or solved with taking into account the temperature dependent viscosity for more accurate solutions. Now let us consider the various geophysical applications of the mantle convection models. These models explain certain observations on the surface of the Earth. The plume-driven model. It can explain volcanic activity such as hotspots like Hawaiian Islands and Yellowstone National Park activities. If we consider the layer convection model, it predicts slower heat loss from the lower mantle. This explains how Earth has been retaining the heat which is entrapped for a long duration, which is nearly 4.5 billion years. This explains the slow loss of heat, without which Earth would have lost all its entrapped heat and would have become barren. Lastly, the whole mantle convection model. It provides the mechanical link between the surface plate tectonic motion and mantle dynamics. It is only the motion of mantle convection which drives plate motions. The whole mantle convection model provides good results and estimates for the plate motion with mantle convection dynamics. Also, the subduction slabs act as primary driver of convection currents in mantle. This is supported by the whole mantle convection model. Thus, we can see that various mantle convection model support various evidences. Thus, it can be understood that the mantle convection includes all these different features from various models to certain extent. Now, let us discuss the conclusions. Mantle convection models are fundamental to our understanding of Earth's internal processes, and various manifestations of such convection dynamics occur on the surface which are observable and give us information about the deep interior. No single model can perfectly explain all the observations of the Earth's surface due to mantle convection. Thus, a comprehensive framework has to be taken into account from features involving all the mantle convection models. The whole mantle convection model explains deep mantle plumes, such as convection slabs going right up to the core mantle boundary. It also explains the efficient heat transfer from the core to the upper regions of the mantle, which are very efficient. However, the layer convection models reduces the heat flow estimates. It gives geochemical evidence of isolated mantle reservoirs. Also, it takes into account of the 660-kilometer phase transition on the flow patterns. This phase transition is a transition in material properties at a depth of 660 km, which the layer convection model utilizes to improve the mantle convection patterns. Thus, the mantle convection model is an excellent example of heat flow processes in the Earth. These are the various references which discuss mantle convection in much more detail. Thank you.